Hello, my name is Nick Asher. Welcome to my linear algebra presentation on the set of all trace 0 4x4 matrices, and more specifically proving why the set is a subspace of Rn. Firstly, to define our set, we're going to say M is all real 4x4 matrices. S is all of those matrices which satisfy the condition that the trace is 0. We're going to recall that the trace is just the sum of the diagonal entries. So we're going to add these diagonal entries, and that is expressed in this equation. This picture is just relating back to what we have. We could say that A is M, which is all real 4x4 matrices. B is all matrices that satisfy the condition that the trace is 0. So then the intersection of A and B would be S. Next, to talk about our space. Since M is all real 4x4 matrices, it's going to have 16 entries, and this R means that they're all real numbers. So to build any matrix with these conditions, there's going to be 16 chosen entries. So therefore, the space would have 16 independent parameters. Next, to talk about dimensionality, we're going to say that since this trace is a linear equation and everything must add to 0, it takes away our freedom of entries because A11, A22, A33, and A44 for our 4x4 matrices all have to add to 0. So it takes away our freedom of entries because we can't have any random combination of numbers. They must equal to 0. And when we have this situation, we're going to say that we have the n-1 rule, where our dimension of S is going to be n-1 because we have one linear equation taking away the freedom of entries. But if trace wasn't linear, the solution wouldn't always necessarily be a subspace, so it is pretty advantageous because it does form the subspace. Finally, to do our three proofs, we need to prove that our set in subspace has the 0 vector, that it's closed under scalar multiplication, and that it is closed under addition. Firstly, to think about that it contains a 0 vector, this is pretty obvious. If we have a 4x4 matrix that's just zeros, the trace of that is 0, so that satisfies our condition. Next, if we think about the addition, well, if we have one matrix where the trace is 0, the second matrix where the trace is 0, if we add these matrices, the part that we're adding for trace is just going to add to two things that equal 0, so it's still going to be 0 plus 0 equals 0. If we do it on the outside, it's going to be 0 plus 0 equals 0. No matter what, we're getting 0 plus 0 equals 0, implying that A and B are in S, and it's closed under addition. For the scalar multiplication, because K can be any real scalar, and we know that the trace of A equals 0, whether we pull it out or we don't, it's still going to let our trace be 0, satisfying our expression. Finally, we're going to go back to the last slide and say that for M, it is going to have dimension 16, which is the same dimension as R16. I just included this because for our conclusion slide, it's going to be good to remember this point right here. Going to our conclusion slide, we're going to say that S is a subspace of M, and there's one mistake on this slide. Can you catch it? Well, you should be able to catch it because it's on the next line, but it's not the subspace of R16. It's a subspace of R15. Hopefully you caught on to that. Remember, we're using the n-1 rule because we have one linear equation that trace equals 0 that's taking away 4 freedom of entries. Thank you very much. If you have any questions, please leave a comment.